Hi everybody, my name is Helena and I'm the Access and Outreach Manager for the Department of Materials at the University of Oxford, and welcome to our very first Making Materials Matter webinar. I will hand over to our speaker today, Bradley Young. So Bradley is a second year DPhil student at the Department of Materials here at Oxford, and he's going to tell you a little bit more about his research and what material science has got to do with nuclear power. So I'll hand over to you, Brad.
Hi everyone, nice to be talking to you. Yeah, like Helena said, I'm a DPhil student here at Oxford Materials, and I'm doing some research into materials for nuclear power. I'm going to try and share my screen. There we go. So that should be working for everyone. Be able to see the intro slide. And yeah, we're going to talk today a little bit about what nuclear power is, why we're trying to develop it, what we're trying to develop, and what the materials challenges that we face in that development are. So firstly, why are we trying to develop nuclear power? And the main reason, as with huge amounts of research that are going on in universities at the moment, is around the topic of climate change. Nuclear power does present a low carbon form of energy production, and that's really important because, like this graph here shows from the UK government, energy supply accounts for huge amounts of our emissions in the UK. And as we start to electrify transport, and we need to produce electricity for cars as well, so we need more energy to be supplied, our emissions from energy supply are only going to increase. So we really need to come up with ways of reducing or even eliminating the carbon that comes from supplying energy. So you've hopefully had a chance to contribute to the ideas page that Helena sent out, and hopefully we might be able to share that now, Helena, because we've asked you for some ideas on what comes to mind when you think about nuclear power. Some interesting things that have come up here. We've got some topics of atomic weapons, nuclear bombs, and things like that, which is really important. I think that's it's definitely something that a lot of people think about when they think about nuclear power. The fact that they share this word and it's very similar technology. But what's really important to emphasize is that everyone who works on nuclear power, we very much work on developing the technology for peaceful uses around the world to provide energy for everybody. This technology is used in weapons as well, but it's by a completely different set of people that work on those kind of things. The Simpsons is quite an interesting one that I haven't heard before. That's a really good point. Yeah, it goes to show that nuclear power is used is used day to day in the world and in fiction as well, in our entertainment as well. We have this. It's very embedded into our lives. It is something that we use. Some of your electricity that you use in your house will come from nuclear energy in the UK. Clean energy source that has a bad reputation. I completely agree. Good short-term solution to global warming because it's already developed. Completely agree. We should. Nuclear power does present some problems. We have things like nuclear waste and things like that, but it is a fantastic resource that we have that we're not making enough use of, especially in the UK. We should be making a lot more use of the nuclear power that we have at the moment. And interesting talking about it being a short-term solution. I'm going to present a little bit in the presentation about something that might be a little bit more of a long-term, the long-term goals for nuclear power as well. Following on from that, we've got quite an interesting figure here that I hope people can have a look at. It's definitely really good. We talk about the fact that it's a low carbon form of energy, and you can see on the right hand side of this graph here quite how much better than things like coal, oil, natural gas it is, and even something we think of as a clean energy source like biomass. And hydropower, we think of both of those as, well, they are both renewable energy sources, but nuclear energy is much better in terms of reducing greenhouse gas emissions than those two. Some people think that nuclear energy is quite dangerous. We have the fact that it's related to the nuclear bombs and things like that, which I'd like to stress that the technology might be similar, but it's a very different group. Nuclear energy, even accounting for some accidents that have happened in the past, is incredibly safe. The number of deaths associated with power from nuclear energy is incredibly low, especially when we compare it to the deaths that are associated with energy from coal, from oil, natural gas, things like that we use a lot more frequently. So I would really encourage you to think of it in a really positive way, really think of nuclear energy in a positive way. It's something that can really help us. So what is nuclear energy? If we go to a slightly more, we've talked almost about the politics and the things like that around nuclear energy and why it should be used, but in a scientific form, what actually happens. There's two types of nuclear energy, and they both revolve around the nucleus of an atom. Now, the way that we produce nuclear energy at the moment in the nuclear reactors that exist in the world is through a process called fission. What happens is we take a really heavy element, normally uranium, and we break that down. By breaking it down into smaller nuclei, into smaller atoms, we can release energy. Anything that is heavier than iron, the element iron, you can break down, and by breaking it down, you can release energy. And that's really good. That's the process we use at the moment. It already exists as technology. There's a lot of ways we can improve it though, but it already exists. The other way is any element that's lighter than iron. If you provide enough force to push the nuclei together, you can fuse two atoms together and produce a new atom. So the diagram here shows two isotopes of hydrogen. So these are two types of hydrogen. We've got one atom of heavy hydrogen, one atom of very heavy hydrogen. They're called deuterium and tritium. We can use enough force to push those together and we form a helium atom and lots of energy. That's one of the really big benefits of fusion, is that the mass of fuel that you have, you produce lots more energy than you do in nuclear fission, which is really, really good. However, nuclear fusion is just in the experimental stage at the moment, and there's loads of scientists around the world working really hard to get it so that we can actually start providing power and energy to the national grid so that we can supply energy to people using this technology. Like I said, there's loads of scientists working on it at the moment, and the reason is that it's really, really difficult to do. Even in nuclear power that, like we said, exists, the fission type of nuclear power that exists, it works at really high temperatures. And the ideal is to get it even hotter, because the hotter you can run a nuclear reactor, the more efficient it is and the more energy you can get out. So we want things to work really, really hot. There's quite a funny story from this weekend. I was having a chat to one of my friends who works in a Formula One team, and he was talking to me about some problems he was having with some of his materials for his Formula One car, because it was his component had to operate at 200 degrees, which he thought was really, really hot. I thought that was really funny, because we're working with metals that have to work, trying to develop metals that have to work around between 600 and 800 degrees, so much hotter than a Formula One car will ever go. And like I said, in a fusion reactor here, we're working with things that are 10 times hotter than the sun, the center of a fusion reactor. So really, really hot, much more than you'll get in a Formula One car. Yes, the other thing, neutrons. So I showed on the previous slide, we can see that when we break these atoms apart or fuse them together, I can move my mouse, we can see the other things we get out. We get spare neutrons that come out of the nucleus of the atom. These spare neutrons come off with huge amounts of energy. That's great, that's where we get the energy from. But the neutrons can fly into the materials that you've used to build your reactor out of, and they can damage them and make them really brittle, which isn't great. There's corrosion. In order to get the energy out, we have to cool the reactor. That coolant can corrode your materials, makes it really difficult to design materials for this environment. And also for both types of the nuclear power, fusion and fission, we have to make sure everything's really safe. There are dangers involved with producing energy of any form, whether you're doing it with a wind turbine, with a nuclear reactor, with a gas power plant. Any of these technologies can be quite dangerous. So we have to make sure they're really safe, and we have to make sure that we know our materials aren't going to break whilst they're in the power plant. The other really interesting thing with a fusion reactor is, like I said, it's really, really hot. It's about 10 times hotter than the sun. What that means is that we have to levitate the reaction. We can't have it touching anything, because anything it touches, it would melt. So we have to make sure we levitate it. And we're quite lucky that the way reaction works, it's charged. It is in a charged gas that we call a plasma. We have to levitate it. I'm going to show you kind of what that looks like now. This is an experimental fusion reactor that's being built in the south of France at the moment. This is a diagram of what it looks like. And for scale, down the bottom right, we can see a person that's been drawn into this image as well. So you can see this person here to show you just how big this project is, how big we have to make these experiments. The reaction, this fusion reaction, happens in this pink plasma in the middle, and it happens in this donut shape around a central magnet. So that's where our reaction happens, like I said, 10 times hotter than the sun. So we need to levitate it. We're lucky that this plasma is charged, so we can levitate it using magnets. And there's 3 different types of magnets that are in slightly different colors in this diagram. We've got magnets that are kind of in this donut shape that follow the plasma around the light blue color. Those magnets, we've got magnets that are shaped a bit like a capital D in the dark gray around the reaction as well, and one big central magnet down the middle in this column down the middle. So we've got lots of magnets to hold our reaction and to squash the reaction together as well. The other place we have trouble with our materials is in what I've labeled here as the structure of the reactor. So around the plasma, around where the reaction's happening, we have this structure, and in that structure is the coolant as well that we need to use. And that's where a lot of our materials challenges come from, is this bit of the diagram that's labeled here in this D shape, the materials we need to use in that region. Okay, so this is an example. I want to talk about how we levitate our reaction, and the way we do it is using superconductors. This is an experiment you might have seen, but I want to show you a little video of it. It's a video produced by a university out in the US, and what it demonstrates is how we use something called a superconductor, which is a material that can carry electrical current without any resistance at all, absolutely zero resistance. These normally work at really, really cold temperatures, which is why in the video here, you can see that there's something bubbling away in the background, and so the superconductor is the black bit in the middle. Around that is probably liquid nitrogen to try and keep the superconductor really cool so that it does carry current with zero charge. And what they're showing here is how a magnet, this silver thing, that is hovering above the superconductor, and it stays hovered there. So there's this really fantastic property of superconductors that we can use them to make sure that something that is charged or magnetic can levitate. And that's what we use to levitate and confine our fusion reaction as well. And so what a lot of researchers are doing, especially in materials departments here in Oxford and across the UK and around the world, is we're desperately trying to make better superconductors. There's only very certain compounds and types of material that will or that could be superconductors. One type that's got a lot of research at the moment is this compound, niobium-3 tin. And this is an example of what a wire of this superconductor looks like. So when we make the magnets, we actually make them by wrapping a wire in coils, and this is the type of wire we use, this niobium-3 tin. So that's what it looks like in real life. And the way we study this is we have to look at it on a really, really small scale and really understand the structure of the material and why that structure leads to the properties it has, and how maybe we could change the structure to make it have better properties. Now, the way they're doing this with superconductors is really, really advanced. And we used a machine called an atom probe, which was developed here in Oxford, and it's really exciting technology. What it does is you can get a needle of a sample of a material, and you can fire individual atoms off of the tip of that needle. And as you fire more atoms off, you can work out what those atoms are, work out where they came from in the material, and you can build up this 3D image, atom by atom, of where all of these elements have come from. And that's what's shown on the right-hand side here. This is an atom probe, some atom probe data from a niobium tin superconductor. So really, really relevant and high-level research. And we can see how different elements, so we've got 4 different elements here. There's some tin, some niobium, some copper, and some titanium. And those different elements go to different places in the structure of the material. So as you can see here, we've got some copper and some tin are forming these lines around the material, and understanding where these lines are, how far apart they are, all of that kind of thing helps us really understand this material and how we can make it better in the future. So going back to another diagram of a fusion reactor, this is one of my favorite diagrams. I really enjoy this Lego model that someone's built. And this is the same reactor that I showed you a picture of earlier. But instead of looking at it in 3D, what we're looking at here is one segment. So imagine an orange segment. We've kind of got one orange segment here. You can imagine loads of these in 360 degrees around this central gray region. This is the core. If we put a segment all the way around the core, we'd make up our reactor. Our plasma would be in this donut shape. what we can see here really nicely is the magnets that would be in blue, the D-shaped magnets, the magnets in the donut shape in these yellow bricks, and the central magnet here in the middle. And the other thing we can see really nicely is these grey bricks in the middle that make up this structure here, which is really important. And that's what we're going to talk about next, is these structural materials in this D shape around the plasma. Now, these are really close to the plasma, so they have to work at really, really high temperatures. And what we need to do, we don't currently have any metals that work at temperatures that are high enough to deal with that kind of heat that comes out of the reactor. So we need to try and design new metals that will work like this. So one option is to take some steel and try and make it better. That's something that some people are working on. Something that I'm working on is ditching steel. We don't think it will work at high enough temperatures, and let's try and come up with something completely new that we think will work really well in these really hot conditions. So this is something we do. We make these new metals. They're called alloys when we mix two different metals together, or more than two different metals together. But in this case, we're mixing two together. Mostly zirconium, which is this top one, ZR, and we mix in with it some chromium as well, which is this bottom. What we do, we melt them together, we mix them together, and then we can cut up our sample, and we can put it in something that's called an electron microscope, which is very similar to the microscopes you might have in school, optical microscopes. But instead of using light to look at your sample, you actually use electrons. And then instead of your eyes, because our eyes can't see electrons in the way that our eyes can see light, we actually use a detector to see our electrons. What we can then do is look at our structure. We can see here how our structure has got these lines in it, and we need to understand how those lines can affect the properties of our material. And we can also use the X-rays that come off of this material to understand where certain elements are more concentrated than others. So what we can see here is that our chromium is really concentrated in some of these regions of our structure, which is really important for understanding how and why our metal works the way it does. The other things we do, as well as just looking at our metal, we can test it. I mentioned that the coolant is a really big challenge in a nuclear reactor. What we do here is we take a little sample, like you can see on our left-hand side. We've got a little sample of a metal we might want to use, and we dip it in some coolant for a really long time and see what happens to the corrosion. Again, we can put it in our electron microscope and look at the surface. So the lighter grey in this image is our metal, and diagonally across the middle, we can see the surface of our metal, and we can see the effect that the coolant has had for corrosion and what the corrosion has done to the surface of our metal, which is really important for understanding why it works, and therefore how can we design something that might resist the corrosion better. Lastly, the other thing is we need to make sure that our material is really strong, and like I said, it has to be safe, so we need to know our material won't break. So we use lots of different types of tests for this, but one that's quite novel and quite innovative, and I wanted to share with you today, is something called a small punch test. So what we can do is take a little sheet of a sample, a circular sheet, like you can see here in the slightly lighter grey, it's called a miniature disc. We take a disc, we squash it between our two dies, and then what we do is we use a ram to apply a force to the disc, and we can measure how much force we need, and we can measure how much the disc bends as well, and we can use that to determine how strong our material is, and therefore whether it will be strong enough to be used in a reactor and make the reactor safe, which is obviously really, really important for any type of nuclear engineering. There we go. So just to sum up really quickly, what we've covered, we've said that we want an energy source that is a low carbon energy source, which nuclear provides, and it's also not reliant on the weather like a lot of other renewable energy sources are. They're really reliant on weather. In order to make nuclear fusion happen, especially, so there's a lot of benefits for fusion over fission. It's safer, it's better in the long term than fission is. We don't have as much radioactive waste. So we really want the fusion technology to work. In order to make it work, we need really good superconductors. We need to improve the superconductors, so we need to understand them. We also need to be able to build the reactor, and the reactor can get really hot, so we need materials that can withstand that kind of heat. In order to do that, we have to look at our materials, understand them, and test them, and then we can design better ones to make our reactors work really well. So that's the end of the presentation. I hope you've learned lots about materials, how we research materials, what materials are, and hopefully a bit about nuclear power as well. If you've got any questions, I'd love to answer them. Please put them in the chat or anything like that, and we'll be able to answer them.
Brilliant. Thank you so much, Brad. That was a really, really informative, quick talk, taking us all the way through the different types of nuclear power and the materials challenges involved in developing new forms. Oh, brilliant. So we've had one question come through already, which is really good, from Maria. How do we make the reactors?
Yeah, making the reactors is a massive challenge. I'll talk a little bit about the fusion reactors, I think, because they're more interesting. They're something that is more of a challenge. Like I said, fission reactors are being built around the world, but they're a massive collaboration. We talk about the material science challenges. There's huge engineering challenges as well, plasma physics challenges, loads of different scientific challenges that we have to overcome to make these reactors. And they're also, at the moment, they're really big and really expensive. So the ones that are being built are kind of international collaborations. This one that's being built in the south of France, it's a huge number of countries are collaborating on this. So there's huge amounts of project management that have to go into it as well, a lot of politics, and a lot of collaboration between a lot of different scientists of different disciplines. So we have to communicate to each other really well and be able to work together on these challenges where they overlap, and communicate with the engineers that will end up building them, shipping components around the world to make sure they're all the right size, they get to the right place, they're not damaged when they get there, or if they are damaged, how damaged are they still usable, all of that. So there's huge numbers of challenges with actually building one of these reactors.
Yeah, and I imagine there's so many different parts as well within each of the reactors, and each one is made in a special way that a certain team knows how to do. So yeah,
it's a really kind of cutting edge piece of science experiment where nothing is standard. Everything we put into a fusion reactor is very novel. Nothing has been made that is this difficult before. So every single element of it is new. There's nothing kind of off the shelf that's been used before that we can really use in it.
That's really exciting, which leads really nicely into another question we've had from Hamish. Do you try and keep this research quite secretive, or is it shared between everyone? I think that's a really good question.
It's a great question. It's a really, really good question. It's really interesting, and it's a really interesting. I talked about the fact that politics come into this a lot, and they really do on this kind of slightly bigger level. My research, like I've been able to share some of it with you today, is not very secretive at all. There are elements of it that might become secretive in the future. And there's an element to this, right, that if someone gets into a fusion reactor to work and produce energy, they can make a lot of money out of that. So there's a lot of things around the bits, those last little bits that will end up making someone a lot of money, and that's when people start to get secretive. However, I think we're really lucky at the moment. We're in a stage of this science where it's so difficult and everyone understands there's so many challenges that the only way these challenges are going to be solved is if we all work together all around the world. And so luckily we're in a great place at the moment where we publish all of our research. Pretty much all of our research is happy to be shared around the world with anyone working on this problem. And we do really encourage kind of collaboration with not just within the UK, but around, like I said, around the world. Lots of different universities, particularly America, Japan are quite big centers for it, as well as France. So yeah, at the moment it's not too secretive. However, as we go towards the future and we start to get closer to building things that will make people money, people are going to start to get more secretive about it.
Yeah, I think that's a really good point. And it's really nice to hear about how collaborative it is, because the thing that works, when science works best, is when we all talk to each other and we all collaborate and we all share our results and work together on problems. And that's really, really true in this sort of research. Brilliant. So we've got time for another question or two, maybe, if anyone wants to add any into the Q&A or the chat. I've got half an hour on that as well. But I have a question that I always like to ask about fusion energy. How long do you reckon it'll be before we have working fusion reactors at a commercial scale, or even before commercial scale?
Yeah, there's a lot of different answers to this, and a lot of people are promising different things. I think I showed some pictures of this international collaboration that's happening in France at the moment, and kind of what the next stage of that will be a reactor that should demonstrate that it can produce power. And I think their aim is to put energy, the kind of international collaboration aim is to put energy on the grid by 2050, I think, if I'm remembering it right. Then there's the UK, we're doing our own kind of side project on the side of that as well. We're trying to make things, one of the ways to get power out is to make your reactor bigger. The UK is trying to do the opposite and make our reactor smaller, and see if we can make it work that way by making it smaller. They have a goal to be producing energy by 2035, I think. But then there's some other private companies that are trying to do, they've got some investment and they're trying to do their own research. They're trying to go even quicker. They're talking 5 years, 10 years, something like that, which I think might be slightly unrealistic. They are trying to get investment, but there's a lot of different aims. Realistically, there's huge numbers of problems to solve, and I think it's incredibly hard to put an estimate on it. I would say that I don't think nuclear fusion we should wait for it to try and solve our climate crisis at the moment. Nuclear fission that already happens, I think we should make much more use of right now. That's definitely something that can help us in the really, really short term. Nuclear fusion is definitely a long-term thing to look at with population growth, and we can scale it up really easily when our population starts to grow. But there are other things we need to do in the short term to avoid the climate crisis.
Brilliant. Yeah, very good point there at the end. Okay, just one final question, and I think we'll wrap things up. Another one from Hamish here. How is the energy, which they're guessing is heat, actually harvested from these reactors?
Yeah, sure. So the energy comes out sort of as heat. So heat is, the kind of definition of heat is energy within particles, energy within atoms and atoms vibrating. The energy comes out of nuclear reactions with these neutrons that we talk about, which are subatomic particles. These neutrons have huge amounts of energy. They will then collide with something, which is the coolant, hopefully. They'll collide with a lot of things. That's why they make our reactor hot. But they will also collide with the coolant that we pump around the reactor. Once they've made our coolant hot, we're pumping that around the reactor, and we can remove the hot coolant, put some new cold coolant in, constantly pumping that. You use your hot coolant to boil some water. Water turns a turbine. Turbine produces electricity. In that kind of way, it's very similar to the way that we produce energy from power plants, coal, gas power plants at the moment, which is why it's so scalable, and it would be very easy to introduce it if the technology is working. It's very easy to put it out onto the grid, which is a bit unlike solar power or wind power, where you have these huge farms that are producing energy. Instead, it's a very concentrated form of energy. It works in a very similar way to conventional power plants. Like I said, you make something hot, which heats your coolant up, and your coolant produces, turns a turbine, produces electricity. And so in that way, it's quite similar to the technology we have.
Brilliant. So I think with that question, we'll finish today. Thank you so much for such a fantastic talk, Brad. That was really great. And thank you for answering these questions.